In this video, we're going to discuss effusion. So effusion is an interesting term, but long story short, it basically means if you have a container and you fill one side with gas and the other has a vacuum, and then you poke a tiny hole in it. Gases, there is no suction. Vacuum doesn't exist. It's not a thing. It doesn't pull stuff in. What happens is those gases are just bouncing around. They're bouncing into other gases. They're hitting the walls. And as they bounce, they might hit the hole or they might miss it. Sometimes they will pass right through the hole and get to the other side. Well, why does a vacuum seem to pull stuff through? Well, it doesn't. There's just nothing going back, keeping the material from getting through. If you have gas on both sides, they both try to pass through, they bounce into each other, or slip past each other, and you don't notice the difference. But when there's a vacuum on one side, you definitely notice when things manage to pass through. What will happen is eventually gases will pass through, and some of them will be going back. They'll bounce around and they'll manage to go back to the other container. But over time, the side with more will decrease, the side with less will increase, and eventually you will have equal pressures on both sides. How long this takes is the idea of effusion. How quickly does your gas move through that tiny hole? How quickly does it find it and pass through to the other side? Effusion is one of the few properties that is actually different between different gases. With the ideal gas law, we haven't had to worry about what the species of our gas was. All of them, for the same number of moles at the same temperature in the same container, had the same pressure. But effusion is different. Long story short, lightweight gases move faster. Heavy gases are slower. Well, what's going on? Remember that all the gases are the same by the ideal gas law. Same pressure, same temperature, same moles for the same volume. But let's think about temp for a minute. Moles are pretty easy. It's just the number of things. Your volume isn't actually the gas, it's the container. Your pressure is how hard they're hitting. Temperature, though. Temperature is proportional to the average kinetic energy. Kinetic energy for a particle is equal to 1/2 mass times velocity squared. Basically, you get higher temperatures if your things are moving faster. Can't really change the mass of a gas, but you can speed it up. So when you put more energy in and it gets hotter, the reason is that it's moving faster. It's hitting things more quickly, transferring more thermal energy from friction on impact. And so it is hotter in terms of temperature. Well, if you have two different gases at the same temp, so you have, say, helium versus argon. Well, helium is 4 grams per mole. Argon is 39.95 grams per mole. It's about 10 times heavier. So when we think of the mass, well, if they're at the same temp, they have to have the same average kinetic energy. But one of them is just more massive. If your mass is greater, your speed must be slower so that your kinetic energy comes out the same. Heavier gases just move slower for the same temperature, compared to lightweight gases, which move faster at the same temperature. And so fusion is one of the few things that's different between the gases. A big object moving slow hitting something can hit with the same force as a lightweight object moving quicker. This is why our pressures are still the same. Even though my argon is moving slower, having a bowling ball roll into your foot can hurt, or having a pickleball roll into your foot probably wouldn't. But if somebody throws the pickleball really fast, yeah, it could still probably hurt a little bit. So the idea with effusion is because of this difference in mass and velocity of those gas particles, the speed at which you will bounce into that hole and pass through is different. To actually calculate out the rate takes a lot of extra data, but what we tend to actually use this for is comparison. We want to know that the rate of gas A versus the rate of gas B. If I have two gases, which one will be faster? This is important if you're mixing gases for reactions. If you're constantly putting gasoline and air into an engine, well, you need to know how big your tubes have to be. You need to make sure you're adding the right amount of each of them. You can't just make two equivalent tubes because one of them is not moving as quickly. The heavier gas is not going to move through the tube as quickly as the lightweight gas. And so you have to adjust them based on how fast you expect them to go. So based on these rates, well, ends up, if I want to do this comparison, the fusions are based on the square root of the molecular mass. The molecular mass of B over the square root of the molecular mass of A. So they are inverted this way. My rate A over my rate B, that ratio is going to be equal to the square root of the molecular mass of B over the square root of the molecular mass of A. Or you can simplify it, the molecular mass of B divided by the molecular mass of A, and take the whole square root. As a result, you can say, hey, how much faster will compound A move than compound B? If we try that for us, how much faster will helium be versus argon? Well, it's going to be the square root of 39.95 divided by 4.00. Basically, it's going to be the square root of 10. 40 divided by 4. Square root of 10 is 3.16. What this tells us is that helium will effuse 3.16 times faster than argon will. So if you had a mixture, if you had a container that had helium and argon, and you open a little port into a side that had vacuum. Well, say these were 50-50 to start with, you're going to end up with far more helium on the other side. It gets over there far quicker. And so you're going to have a much bigger percentage of helium than of argon on the other side. You can effuse for a little while and then seal it, stopping any more getting through, and you will have a greater percentage of helium versus argon. In fact, you could do this again. Pump out the original container, make it the vacuum, reopen that port. Well, now my mixture is starting at some other percentage. Depending on when we stopped it, it could be at various places, but we're going to say it's 70 and 30 for our purposes. Well, they're both going to pass through, but that helium is going to pass through faster. And then we'll seal it back up. And now it might be like 80% and 20%. We are losing some gas each time. There's stuff left in the other chamber. But we are purifying the faster moving gas. In fact, what's left in this chamber is going to be more argon than it started with, because a lot of the helium left. We're actually purifying the argon in the other chamber. This is how we actually purified uranium in the first place. Uranium-238 versus uranium-235. In the Manhattan Project, we turned them both into uranium F6. Uranium 6 fluoride, or uranium hexafluoride, is a gas. The only difference is a very tiny mass difference between these two. 349 grams per mole, 352 grams per mole. Those isotopes weigh just a tiny bit different amounts, which means you could purify them. Square root, let's do 235 uranium over 238 uranium. That's going to give us our 238 on top, 352 divided by 349, 1.017. So the lighter weight uranium moves about 1.7% faster. This does mean that you can purify it over time. You just have to do a lot of these back and forths. In fact, in the Manhattan Project, what they actually did was they had 2,142 separate 48-foot effusion chambers. They did this many, many times with very big chambers. In fact, they just let it run. They had one giant chamber, had lots of routes, and then at the end, they plugged it into another giant chamber, which plugged into another one. They just did this back and forth. All the gas went in at the start, and it spread and spread and spread and spread. And by the end of 2,000 some of these, they collected the first gas that came out, and it was much higher in uranium-235. They then turned it off, just took those original first ones coming out that were the most pure, pumped down the entire device with a vacuum, recollected it, and did it again. Doing this several times over, they could collect enough uranium hexafluoride of the lighter weight that we went on to make the first nuclear devices. So effusion has its uses. We don't really do this with it anymore, thank goodness. But it's just another property of gases to know. It is one of the few properties like density that is actually different between different gases.